Good evening, everyone. Myself, Chaitanya Kumar from Department of Electrical Engineering, IIT Madras, and welcome to the fourth week problem-solving session of analog circuits. I hope every one of you have gone through the lectures of this week, and right now, very few students are there. Almost only one student is there. Do you have any doubts or do you have any uh, issues that you want to get cleared up, maybe in the previous assignments or in the course content that you want me to explain? If it is there, we can discuss that, or I can start my own questions. Okay, so if there is nothing for you guys to discuss, so let's start with a few concepts that we can work on. And last time we were discussing about second order filters, right? So we were seeing how to emulate inductors and all those things. So we will build up on that concept only. So let's start with how band pass filters are built. Band pass filters. So basically, what is a band pass filter? It is a filter which has a frequency response 0 at DC, and then it peaks around some particular frequency that makes its pass band. And then at very high frequencies it again drops down back to 0. So this is how a band pass filter works, and so how we get it in practice, let's try to see it. So let's focus on this particular filter. So let's say we have, instead of voltage, we have current as input, and we want to see what frequency response we get for the trans resistance function, that is V naught by In. So what will V naught by In constitute of? So we have an L, an R and C over here. So what will V naught by In constitute of? So we need a band pass filter, right? Let's see if this particular thing gives us a band pass response. How do we get a band pass filter? Can any one of you tell, like, what will be the at very low frequencies, what will be the output voltage? Let's say In's frequency is tending to 0. In of F tending to 0. At those low frequencies, what will be the voltage developed? So at those frequency, the voltage that will be developed is so since our L behaves as short circuit at DC frequencies, at low frequencies. So in that case, the voltage that will be developed will be 0, and at very high frequencies, the capacitance will become short circuit. So the voltage developed across the capacitance will also be 0 at very high frequency. At very high frequencies, also the voltage will be 0. At intermediate frequencies, when all RLC are not short, in those frequencies we will get some voltage. And if you guys might be familiar with the concept of resonance. So at a frequency of f naught is equal to 1 by 2 pi root LC, you will get the maximum response. So let's try to write its response, and then we'll try to see if so it seems like a band pass filter. We will see if this is feasible or not. So let's try to write the response of this. The impedance of L will be SL, R we will have as R, and the impedance of the capacitance will be 1 by SC. Correct? So the V naught by I in will be equal to the impedance looking inside the filter. So what will be the impedance? It will basically be the parallel combination of the three impedances. So we can write it as follows: 1 by SL plus 1 by R plus SC. So let's try to simplify it. So what we will have is so we will have SL times R SL times R plus SL plus S square LCR. Correct? So let's take R as common from this complete thing. So we get SL, just a minute, SL divided by S square LC plus SL by R plus 1. Correct? So if we just multiply it and divide it by R, so we get this thing over here, right? Now let's see, this is what we have as V naught by I in. Let's try to see if this transfer function makes sense. So we can see, right, at very low frequencies, that means at DC, your inductor is supposed to become short, so the voltage developed V naught will be 0. And we can see it from this expression as well. If your S is 0, the overall voltage developed at very low frequencies will be 0. At very high frequencies, this 1 by SC term becomes 0. That becomes a short circuit. So again, at very high frequencies, the voltage developed will be 0. In this particular expression, so at very high frequencies, we can see that the S square term will dominate in the denominator. So S upon S square, we will have something like S upon S square, and as S tends to infinity, S upon S square tends to 0. So at very high frequencies also it goes to 0. Now let's see what happens at, so let's substitute it by S by j omega. So we get R j omega L by R divided by minus omega square LC plus j omega L by R plus 1, right? So let's see what happens at omega equal to 1 by square root LC. Okay, so if omega is equal to 1 by square root LC, in that case, what will happen is R j by square root LC L by R divided by, now this omega square LC at omega is equal to 1 by square root LC will become 1, right? So it's minus 1 plus j L by square root LC times R plus 1. So this 1 and 1 will be cancelled with each other, and we will be left with R. Okay, so what we have is V naught is equal to R times IN. Correct? So in this particular thing, so we saw that from the expression at omega naught as 1 by square root LC, we get V naught as R times IN. Now let's see if it makes sense. So you guys are aware of something called resonance, right? Can anyone will anyone like to comment? You guys know, if you don't want to speak, if you're not comfortable in speaking, you can also type in the chat window, and that also should be okay for me. So if you guys interact, it will be better for me, and it will give me more motivation to explain new concepts to you. So you guys are familiar with the concept of resonance, is it? Series resonance, parallel resonance. Okay, so I think you guys might be familiar because most of you are, I think, BTech second year, and resonance is a concept that is taught in high school only, right? So basically, what we see over here is there is a parallel resonance in this circuit, right? So at the frequency, at the resonant frequency, and what will be a resonant frequency? Omega naught will be 1 by square root LC. So at that frequency, what will happen? Your LC combination will act as an open circuit, and only impedance that looking in impedance that you will have over here is 1 by R, right? So from there you can see that In times R will become equal to V naught at the resonant circuit. The same thing we are getting from this expression as well. When you substitute omega as 1 by square root LC, the trans impedance function that you get from input current to output voltage is equal to the resistance. So this is clear. So this basically proves that whatever equation we have written is correct equation, right? Now, one problem that is there with this equation is that so we have got our band pass filter. So how the frequency response of this band pass filter looks? So on y axis we will have V naught, on x axis we will have I in, and we will get something like this. Okay, so here there will be omega naught, and what is the V naught that we get over here is R times I in. Okay, so this is our band pass filter that we needed. Now the problem with this band pass filter is the current is the input is in current form, right? But let's say we want a voltage by voltage gain. So we will somehow need to convert. So we know this can act as band pass filter. Now what we need to do, we somehow need to convert a voltage into a current that can be passed to this particular impedance, and we can get the band pass filter we desire. Okay, so let's try to do that. So how can you convert a current into a voltage into current? You need to pass it through a resistance, right? So let's say I had a resistance of value R connected to ground. Now if I give some input V in over here, so what will be the current that will be flowing from through this resistor? So I in will be equal to V in by R, correct? So this current somehow we need to push into the parallel combination of RLC that we saw over here, this RLC circuit, right? So how we will try to do that? Let's try to figure it out. So what we will do is this is a real ground, but let's say if this was a virtual ground also, still our we could have got that current. And if there is a virtual ground, we can actually use the current that is flowing towards that virtual ground and send it to a impedance and get some voltage out of it. That is the concept of op-amp based negative feedback circuits, right? So let's say we have this circuit over here, we have R over here, we give an input of V in to this, and then we have some impedance Z in, and we take the output over here. So this is a classic inverting amplifier, right? And what will be the gain from V out to V in? That will be equal to minus Z in by R, correct? So what happens in this? Your V in gets converted into a current of V in by R, and then that passes through this impedance of Z in. And since on one side of Z in we have 0 voltage due to the virtual ground, on other side of V in output on other side of Z in we get a voltage of minus the Z in times whatever current is flowing through that, right? So if that is the case, now we saw with this analysis that a parallel RLC combination gives us an impedance that is band pass in nature. So we can just substitute that parallel RLC over this Zin, and hopefully we will get our band pass filter that we required. So let's try to do that. So we have this resistance over here, an inductance L, and a capacitance C, right? And then we take the output here as V0. Okay. So this is how the circuit will look. Now let's see what. This is basically the Zin that we have put over here. What was the Zin? We calculated over here. This is the required Zin. So if this is substituted in the inverting amplifier's formula, what do we get over here is SL by R. So let's put the Zin first. So it's basically R divided by R times SL by R divided by S square LC plus SL by R plus 1, right? And this is the Zin. So minus of this divided by 1 by R is our transfer function from input to output. So what we get over here is minus SL divided by R, this overall thing divided by S square LC plus SL by R plus 1. Correct? So this basically over here we get a band pass transfer function from a voltage to voltage. So let's recap a little bit. We saw that if a current is pushed into a parallel RLC network, this will give us a current to voltage transfer function that is band pass in nature. And where will it peak? It will peak when L and C becomes come in parallel resonance, that is at a frequency of 1 by square root LC radian per seconds, and at that frequency we will get maximum impedance, that is of R, and so basically this and at very low frequencies L will become short, so V0 will be 0. At very high frequencies C will become short, so again V0 is 0. Okay, but then we said that since this is a current to voltage transfer function, and in our most of the circuits that we have seen, or most of our practical circuits, we want a voltage to voltage transfer function, we want a voltage to voltage filtering. So we needed to somehow convert this current into voltage. So what basically can be done as a very simple way to convert current into voltage is to pass voltage into current is to pass the voltage through a resistor, and that voltage divided by resistor will give you the current. So what we thought is that let's say there is a resistance of value R connected to ground. If we put the value of Vn on that resistance, the current that we will get is In is equal to Vin by R. Now this resistance, this current we somehow needed to push to an impedance to the so basically to that parallel RLC network that we created, right? So the best way to do that is to instead of connecting this resistance to a ground, to an actual ground, we can connect it to a virtual ground of the op amp. So that's what we did over here, right? So this current Vin by R will flow into this virtual ground, and from this virtual ground it will flow through this Zin, and at the output we will get voltage of Vin times minus Zin by R. Now if we substitute the parallel RLC network instead of this Zin, and then we will get a band pass filter that filters an input voltage and gives some output voltage. So this is a full system that we explored so far. Now the problem that occurs is, so we generally want, so you might have heard about this concept of integrator. So basically we mostly prefer integrated circuits, right? Why do we prefer integrated circuits? So let's see how we will build this. Building this circuit, building this circuit in an IC. Okay, So why do we need integrated circuits? Again, I will ask the students of this group. So in this class, what is so fascinating about integrated circuits? Or at least you guys have seen integrated circuits in your life, right? In your maybe your labs, maybe your, like, you might be doing some experiments in your BTech, right? So you guys can chat. You guys can post your queries or comments or whatever I ask those answers in the chat window as well. And from that, at least I will be aware that yeah, some of you are actually listening and trying to understand what I'm saying. So again, I'll ask. You guys have seen integrated ICs, right? Those black color small devices that maybe you put on breadboard or something. You guys have seen them, right? Okay, I assume that you guys have seen that because, of course, you guys most of you are in BTech second year, possibly. Yeah. Yeah, one of you said that, yeah, you have studied op-amp as an integrator. So like basically what we want is there are two ways to build circuits, right? One, you can take an op-amp, you can take a capacitor that comes from a market, you can take a resistor that comes from a market, you can take an inductor that comes on a from the market. You can put them in this particular configuration on a breadboard. You can give the input, you can plot the output, right? But what happens is this basically takes a lot of space, right? So let's say you wanted, you know your phone's required filtering, right? For example, you guys have heard radio. Every one of you have heard radio. And nowadays, you hear radio on your phones also, right? So basically, if you, let's say, want this band pass filter, so why do you need a band pass filter in a radio? Can anyone comment that? So basically, what happens is that you guys, let's say you tune into some particular frequency, let's say 98.3 FM. Okay, we are talking about frequency modulation over here. Let's say you tune into 98.3 FM. Now, let's say there is an antenna in your phone. Now, at that antenna, all the complete frequency band, I think for FM it is from some 90 megahertz to some 108 or 110 megahertz or so. So that complete frequency band will come on this antenna, right? Now you want to particularly hear 98.3 megahertz FM, right? Now that 98.3 megahertz, yeah, correct, to specify a certain range of frequency. So you want that only that 98.3 megahertz, whatever is coming, whatever signal is there on it, that 98.3 megahertz, only that should pass, and all other frequencies should be rejected, right? So that's why you need a band pass filter on your phone in order to select a range of frequencies. Okay. Now let's say you wanted this band pass filter on your phone, right? Now like building it with discrete resistors, capacitors, inductors, and op amps, and putting it on a breadboard or let's say even a printed circuit board will consume a lot of area. And if it consumes a lot of area, then basically your phones will become very bulky, right? But nowadays you see there are very sleek designs. Even some phones are coming, some flexible phones are coming which are just like paper, right? So in those so basically you want the sizes of these band pass filter to be very small, very compact. So in order to do that, you what you do is you basically take one IC. So what does so you move to a solution of integrated circuit. What an integrated circuit mean is you have one particular wafer of silicon. On that only you will let's say by doping. So I hope you understand the concept of silicon, like p doping, n doping, all those things you understand, right? Yeah, so basically what you will do is like in this silicon only at in some area you will just dope it. Let's say you will dope it with some particular concentration of doping so that this becomes a resistor. Then in some area you will make let's say metal oxide semiconductor kind of structure. So there will be a metal over here, in below that there will be some oxide, and below that there will be some substrate, and you will make a capacitor. So on a on a single silicon wafer, you will try to build this complete circuit instead of getting those capacitors, resistors, inductors from a market and putting it together on a breadboard or a printed circuit board. Okay, so you will try to build the complete circuit on a small single component. Okay, so that is basically called integrated circuits. Now capacitors can be built easily on wafers. Okay, and so can be the resistors. All for capacitors, what do you need? You basically need an insulator sandwiched between two parallel plates, right? So let's say so that can be easily built. I think most of you might have studied the concept of metal oxide semiconductors, right? MOS capacitors you might have studied, or CMOS technology you might have heard of, right? So correct. So basically, what is a CMOS? So MOS, it's metal oxide semiconductor. So metal is a conductance. Okay. Then you have a oxide, and what is that oxide made of? Can someone comment? So this is a metal, SiO2. Okay, silicon dioxide you have, and below that you have this silicon substrate. So silicon also, if you dope, it becomes a conductor or a semiconductor. So between two conducting plates, you have a oxide and insulator, and that will behave as a capacitor. So capacitors also are easy to make on a wafer. But how do you make inductors? So like, what is the principle of an inductance? You need to coil it so that flux can be stored inside that, right? So you need certain amount of coiling so that when the current flows through that, AC alternating current flows through that, some flux will be generated in that. So you need those coiling. Now making those coils on an integrated circuit is an extremely tough affair. Okay, so let's say how will you want to make those coils? So definitely this is a planar circuit, right? So so three-dimensional coils you cannot make. You cannot make a like three-dimensional helical structure. So you will need to make something like this. Now this will consume an extreme amount of area. It will so two things will happen. One, this will consume an extreme amount of area. Other, there will be so this coil will be, so let's say in discrete components, what do you have? In discrete components you can use a very thick wire so that it doesn't has its series resistance of its own, and you get pure inductance. But that won't be possible in your integrated circuits. You can't have very thick wires. If you have very thick wires, then your complete area will be taken by an inductor only, and you will again lose too much amount of area. So you will need to have thin wires. If you have thin wires, some series resistance will come. That will drop the inductor's quality factor, and that may alter the frequency that you need. So making inductors is not a very easy affair on your chip. So what you need to do, so you have an op amp, so you need to somehow emulate an inductor. So not have an inductor, but have some circuit that can give you the property of inductance. Okay, so what we will see, like how to make inductorless band pass circuit. So till now we saw that band pass circuit can be made by parallel RLC combination. So let's see how we make inductorless band pass circuits. Inductorless band pass circuit. Okay, so what do you mean by inductorless band pass? Like somehow like instead of inductor we want something that can behave as an inductor. So how does an inductor behave? So if let's say my L is connected to ground and I push a voltage V in over here, what, and this is let's say L, what will be the current that will be flowing through this voltage V in? So the current, that will be flowing over here is V in by SL, right? Correct. So we need something we need to make a circuit in which if we put a voltage V in on one side of the inductor, on the other side near the ground, or maybe through the complete particular circuit, we get a current that is equal to V in divided by some impedance, and that impedance should increase with frequency. Correct. So here you can see this SL is the impedance, and as the S increases, the frequency increases, your impedance increases, right? So you need to emulate a circuit like that. So basically, in the band pass filter that we made, how does this seem like? So we have this resistance that is easily made on the IC. We have this capacitance that is also very easily made on the IC. Apart from that, we had this inductance. So let's say some V out was there. If this V out is there, this current is V naught by SC. Okay. So this particular function we need to generate by some other means. Okay. Now, what approach we will take is, so we know that we can't directly, V naught divided by SL. Okay. So we know that we can't directly get some device that can give you this kind of current, V naught divided by SL. So we need to somehow do some tricks to get that. Now, can anyone, so we can't get a current that is reducing with frequency. We can get a voltage that is reducing with frequency, right? So we can get something like V naught divided by S times some factor, let's say alpha. Okay. Let's say this voltage we want. Vx is equal to V naught divided by S alpha. So what kind of structure that you guys have studied so far can give you this particular voltage? So what is this? 1 by S, 1 by S, or let's say for even more familiarity, let's call that 1 by SR. So where do you see this kind of transfer function? In which particular circuit that you have studied so far?
Sir, RC circuit.
Yeah.
RC low pass circuit.
No, but in RC low pass circuit, I think it's 1 by
Simple.
1 plus S by RC, right? Yeah.
Yes, sir. Yes, sir.
So, like apart from that, 1 by SRC, how you can get? Think about some op-amp based circuit that you might have studied.
Sir, integrator, op-amp integrator equation.
Correct.
Final
Exactly.
expression.
Exactly. So with an integrator, you can get something like this. Okay. So let's say I put an, so I don't have the inductor over here, right? So let's say we had this resistance over here. We had this V in. We had this resistance. We had this capacitance. And some voltage V naught was getting developed over here. And we put an integrator. How does an integrator look? We have a resistance at its input. So let's call this R, or maybe R1. And we have an op-amp over here and a capacitance at its feedback, right? This is how an integrator looks, right? Correct. So here we will get V naught by, let's call this C1, let's call this R1. V naught by C1 R1. So we got a voltage that is dependent on, that is reducing with frequency. But what we wanted some current to flow in this particular direction towards the virtual ground. That reduces with frequency. So how do you convert current into voltage? Sorry, voltage into current. We have a voltage that reduces with frequency, but we want some current that flows into this particular virtual ground that reduces with frequency, and that will do our job. So how do you get that? So we have a voltage, we want a current. Yeah.
Applying KCL at node.
No. You want a physical current. So you have some voltage over here, but you want you want to connect, let's say, some device in the between that can give a current proportional to this voltage.
Okay, sir, not getting, sir, no idea.
Okay, so if let's say there is a resistor, if you have some voltage over here, what will be so what will be the current? V by R, right?
Yes, sir.
Yeah. So same thing we need to do. We need some. We need to make this. We need to make this voltage into a current, and that current should go into the virtual ground of the op amp, right? So we can directly connect a resistance, right?
Yes, sir.
Okay, but one problem still exists. So here you saw that in this case, when a voltage V0 is applied on this, the current is flowing in which direction? Towards the virtual ground, V0 by SL. Correct. Now,
Yes, sir.
so is the whatever I have written, is the sign of this expression correct? If V0 is over here and it passes through this integrator, will it be will the sign whatever I have written, is the sign correct? So for this RC integrator, the sign will be negative over here, right? It's -1 by C1R1, correct? So what happens is, now if you directly connect a resistor between the two, let's call this R2, what will happen? The current will be proportional to will be inversely proportional to frequency. That functionality we achieved, but the current will be flowing in the opposite direction. So what will be the current flowing here? V0 by SC1 R1 times R2, and that will be flowing in this direction. But in the original circuit, we wanted the current to flow in the inside the virtual ground. It's moving away from the virtual ground, right? So what do we need? We need some inversion between this output of the integrator and between the resistor. So we can add a this -1 over here. Okay. And how do you get a gain of -1? What do you do to get a gain of -1? So basically you have studied about inverting amplifier, right? Inverting amplifier. So in this inverting amplifier, if you had, let's say, R1 and R2, let's call this V1, let's call this V2. Okay, so V2 would be equal to -R2 by R1 times V1. Now if both the feedback resistance and the input resistance are equal, in that case, what you will get is R2 and R1 will be cancelled out, and you will get V2 as equal to minus of V1. Correct? So, if the resistance of these two resistors, the input and feedback resistor, are made same, then you can get an inversion. So the final circuit over here will look something like this. You will have R, you have some capacitance C, you had a resistance R, and how did you make your inductor? Through R1, going through this capacitor C1, passing it through inverting amplifier, and then pushing it inside through R2. Okay. We will draw this circuit a little cleanly over here. RC, and then you have an R1, C1, and it goes like, let's say you have R over here, and R over here, and then it goes through R2. Okay, so here is your output voltage. So if this output voltage is V0, so here you will get as minus V0 by S C1 R1, and that becomes minus V0 by SC1 R1. So plus V0 by SC1 R1, and the current that will be flowing over here is V0 by SC1 R1 times R2. So this complete circuit over here emulates an inductor. Correct? Now this inductance, what will be the value of this inductance? The inductance will be C1 R1 by R2 is the L equivalent. Okay. So if let's say you wanted some inductance of value L, you will have to choose your C1, R1 and R2 in such a way that this expression leads to that particular inductance. Okay, now we have made the circuit. Now we need to verify whether whatever we have made gives us the actual band pass filter at this node V0 or not. Correct. Only then we can say that okay, whatever we have built is actually correct, and it's not just some imaginative thing that we have come up with. Okay, so let's try to now next thing what we will do is we will try to find out its transfer function from input Vin to output V0. So the current flowing over here is Vin by R, and here the current I have already written. The current flowing inside this virtual ground through the resistor R2 is V0 R2 upon SC1 R1, and this can also be written as V0 by SL equivalent. Okay, so this V0 by SL equivalent, and this L equivalent is equal to C1 R1 by R2, right? Now what is the voltage flowing from this node? It's V0 by R, and the voltage flowing from this node is V0 by SC. Sorry, V0 times SC. Okay. So if these voltages are known to us, so what we will have is V naught by SL equivalent plus V naught by R plus V naught times SC plus V in by R is equal to 0. So what I have done? I have applied Kirchhoff's current law on this particular node, the virtual ground. Correct. So what I get from here? So I get S square L equivalent times C plus SL by R plus 1 divided by S times L equivalent is plus V in by R is equal to 0. That implies V in V naught by V in is equal to minus SL equivalent by R divided by S square L equivalent times C plus SL by SL equivalent by R plus 1. Okay. So here you can see that the band pass filter that you got with an inductor can also be made by emulating the inductor using some combination of active RC circuits, right? Now this can easily be integrated on an IC. There is no so in fact the amount of area that you might wonder that okay, I have two resistance, two op amps, one capacitance and one resistance over here instead of that inductor. But to be very fair and to everyone's surprise, all the area of all these devices that I have put over here will be still lesser than the inductor that you would need to put on the chip. So that's how tough it is to make an inductor. So an inductor will take much more area than what this complete circuit over here will take. Of course, there are challenges of making these kind of circuits. So the biggest challenge is that at least when you had that passive inductance, so you don't need to. So these op amps consume power, right? Op amps are active components, and active components can only give you gain, or active components are supposed to give you gain, right? And gain can be achieved only if the input power is greater than output power. Now, from where will that power come? That circuit cannot generate power itself, right? So you will have to supply some additional power source, let's say a battery, to the active component so that it can actually give you the gain that it requires. So the op amp, these op amps consume power. Now this inductance was there, this was a passive component, it didn't consume any power. But over here, instead of one op amp, now you need three op amps. So the power almost tripled, not exactly tripled, but yeah, it increased. Like the power consumed by this op amp might not be equal to the power consumed by the other two op amps, but the power consumption certainly increased. Other thing what increased is, so are you guys familiar with the concept of noise? Thermal noise. Do you guys know the concept of thermal noise? Anyone? Okay, so basically what happens is that we assume that if we give some input to a resistance and of value R, the current will flow as V in by R. So what happens is, if you put a resistance across a bunch of electrons, the electrons start moving in one particular direction and you get that current. Okay, but that is just the average current that you are going to get. It won't be actually V in by R. So basically electrons won't flow completely in one direction. There will be so average, on an average they will be flowing in one direction and average current will be V in by R, but there will be some random motion, like some electron will collide with some other electron, and so these kind of things will happen. Okay, and as the temperature increases, this randomness also keeps on increasing. So what will happen is, along with that V in by R, you will get some noise on that. So there will be some V in by R plus some Vn. Okay, and this n will be random in nature. Now let's say you had this complete circuit, and you give V in, you assume that current V in by R will flow here, right? But V in by R is not flowing, some noise is flowing. Similar case will be there from all the resistances. So here you assume that V naught by R will flow, but V naught by R some plus some noise of this particular resistor will flow. Okay, so more and more resistances are there, the circuit becomes more and more noisy. At the output, you assumed that you will get, so if you give V in as a sine wave, you will get output as this transfer function multiplied by that sine wave. But that won't be the case. Along with that sine wave, you will get some amount, you will get a large amount of noise as well. So what will happen? The final output will basically have some signal to noise ratio. Let's say you might have so noise in physical sense. Let's say you hear to your FM, right? And when you hear to your FM, most of the time the voice is very clear, you can understand what that guy is saying. So at that time, the noise that is there with that voice is so less that your ear can't detect it. But sometimes you might have heard some shh kind of stuff, right, along with whatever the other guy is saying. In that case, the signal to noise ratio of this complete signal is very bad, so that you can hear that noise. Sometimes you can't even hear what the other person is saying, you are only hearing the noise. In that case, the signal to noise ratio has actually become less than 1. That noise has become larger than the signal. And you have to deal with these kind of problems when you are working with resistors or maybe transistors. Okay, but it so turns out that the energy storing elements, the capacitor or the inductor, are noiseless. Okay, so what happens in so here actually physical motion of electrons is happening, that was causing the noise, right? In capacitance, you don't have the actual current, you have the displacement. I think you guys might be familiar with the concept of displacement current, right? In Maxwell's equation you might have studied. You have the displacement current, and that's radiation that can't generate noise. Okay, in inductance you have resistance-less coil. Okay, that basically generates flux, and that's how it stores the energy. So there is no noise. Okay, so energy storing element don't have noise, only the resistors have noise. So in the above circuit, when there was only RLC over here, in this case there were two resistors, right? So the amount of noise that was getting generated was small. But in this case, you have how many? 1, 2, 3, 4 resistors and 5, 6. 6 resistors are there. So the number of noise generating elements have increased by 4 times. The number of power consuming elements have increased by some 3 times. So there are definitely problems that you need to deal with it. But what benefit do you get by doing this? The benefit that you get is that your device sizes are becoming small. Okay, and in today's day and era, you can increase battery size. Okay, you can increase battery life by many ways. You can charge your system, so power consumption, you can process, you can do some digital processing to reduce the noise. Okay, but you need small devices, you need small phones, you need smaller you need to have wristwatches, smartphones you need. So you need to actually constrain the space is actually a large constraint. So even though there are problems, but there is very much research going on in how to reduce noise, how to reduce power. But integrating the circuit is actually necessary, and integrating the circuit reduces the area, and the area reduction can reduce the size of the devices that you are using. Okay, so this is a very interesting topic. If some of you guys, let's say, try to build your career in analog electronics, then you guys can take these kind of research topics, that let's say how to reduce the noise of your band pass filter, or how to reduce the power consumption of your band pass filters. And band pass filters, let me tell you, are very important things, because like integrated band pass filters that can be integrated on chip, because most of the signal processing is only about filtering. You need to filter some radio signal, and to or like maybe some RF signal, maybe Wi-Fi, anything. You need to filter it out. So this filtering is a very important concept, a backbone of analog electronics. And if you take up analog electronics as your career, you will be mostly dealing with optimization of these integrated circuits, optimization of these particular kind of stuff. So any doubt till now? Okay, so at least you guys are can you guys comment that whether whatever I am teaching, are you understanding that, are you not understanding that, shall I go slow, fast, is this too boring? Can anyone of you comment on something? Okay, I'll assume that you guys are listening, so let's keep on going. Okay, so till now we studied one kind of circuit, right? So let's see from where we started. So we started with the basic concept that we wanted to push a current into this parallel RLC network, and to push the current, we took the way of this pushing the current to a virtual ground. Now this is not the only way. So you guys have studied about transistors, right? So you know that let's say you have a transistor, you give some voltage over here, you get some current at the output. So the small signal analysis, you guys are familiar with the small signal analysis of the transistors? Is small signal analysis understood by you guys? Okay, so okay, if small signal analysis is not clear, so let's assume there is a device, there is a voltage controlled current source, and let me tell you, this voltage controlled current source you routinely make in practice. So what happens in voltage controlled current source? You give a input voltage of V in, you will get some current as I out. And what is I out is equal to GM times Vn. Okay, so this kind of circuit is very easy to make in is very common to make in analog electronics, and we will not go into details of how these circuits are made. So let's say this device is available to you. So what you could have done is, you could have pushed some V in through this, and what is this called? This is called a transconductor. So what happens is, if you push this, so what you will get, V in by GM, and you had a parallel RLC network, and let's say this resistance was equal to 1 by GM. Now you guys understand. So what is the units of GM? So from here, can you tell what is the what will be the dimension of GM? Mhos or Siemens or whatever, correct? So it's basically reciprocal of resistance. So if V in by GM I am giving, let's say the resistance I am choosing as 1 by GM. So in that case, what will be my V naught by V in? So it will be okay. All this V in by GM will flow into this this RLC network. So my V naught will be V in by GM times its impedance. And what is its impedance? We wrote it over here, right? Let's copy this. Now this resistance can be so resistance, as I said, is basically equal to 1 by GM. So we have V in by GM times 1 by GM. Sorry, this, yeah, V in by GM times 1 by GM times sorry, this is not V in by GM, this V in times GM. SL times GM divided by S squared LC plus SL times GM plus 1. Okay, so final V naught by V in you get as SL GM S square LC plus SL GM plus 1. Again, this is a band pass transfer function. So you have, if you have this kind of a transfer function in this form is always a band pass transfer function. Okay, so in this band pass transfer function, again, your resonant frequency was 1 by square root LC, and other terms we can calculate. Now again, like how do we emulate this inductor? We saw one method where we used an op-amp based circuit. Now in previous lecture I had, so any one of you had attended the previous session of the previous Tuesday, that is on 11th February. Okay, so there I actually introduced a concept of gyrator. Okay, so instead of making this inductor by an op-amp based circuit, we can also make this inductor using these transconductance and capacitances. So how did that look? I will quickly go through that concept once more. So again, what did you wanted? So if you had some voltage V over here through this inductor, you needed a current of V by SL. Okay, so how did we make it? So again, the same concept. So we can make a voltage. So exact same concept as we did it for this building this particular circuit. We will assume the same concept. So we know that we can't make a current directly that is inversely proportional to the frequency, but we can make a voltage that is inversely proportional to the frequency. So how we will make that voltage? Through an integrator. Now integrator in with op-amp we saw that was like this. So if we have some V over here we will get some V by RC. In case of this transconductor based circuit, the integrator can be made by this thing. So if you have GM over here, if you push it to some capacitance called C, let's call this GM1 and C1, and this voltage is V. So this what you will get over here, GM times V by SC1. Okay, so GM times, so this current is, so GM times the impedance, and sorry, the current times the impedance. The current is GM times V, that is flowing into an impedance of 1 by SC1. So the voltage you get over here is GM times V by SC1. So this is how you get your you get your current, you get your voltage that is inversely proportional to frequency, which is through an integrator. So if with active RC, so this is also an integrator, this is also an integrator. This is made by an op amp, so this is called active RC integrator. And this is called GMC integrator. So both of them have their own pros and cons, in terms of the noise that we discussed generated. Then there is something called total harmonic distortion. So if you give some input as some frequency, you will get harmonics of that frequency due to a phenomena called non-linearity. So that total harmonic distortion of these two things are different. All those things you will learn in like advanced level courses, but for now you can just remember that, yeah, both of these things will do the job for you, but how well the job they do, that will depend on the that is something that is beyond the scope of this course, so we won't go there. So at least now you know that this integrator is made. Basically what you can have is whatever voltage you are giving, if you give it to some integrator, you get the voltage as output as V times GM times V by SC1. Okay, now this voltage you want to convert to current. And how did we see the phenomena of current conversion in this transconductor based circuit? You give some voltage at the input of a transconductor, at the output you get the current required. Okay, now you can put an integrator over. You can, if you, let's say this voltage you want to convert to current, you can give an, so this was GM1, let's call this GM2, and this is C1. Okay, now this current will flow in which direction? This direction. So what direction, what current we will have over here? GM1 GM2 divided by SC1 times V. Okay, now if this current flows in this direction, that does not serve our purpose well, because we wanted a current that will flow in the opposite direction of the voltage applied. Okay, so instead of a positive transconductor, we will need a negative transconductor, and this is also fairly easy to make. The details of the circuit we won't go into details of the circuit, but let's assume that this can be made. So if we connect it like this, this complete thing will behave as an inductor, and your equivalent inductance will be GM1 GM2 by, sorry, it will be C1 by GM1 GM2. What you had over here in this case, you had C1 R1 by R2, and in that case you have CM GM1 by GM2 as your inductance. Just a minute. Yeah, sorry, it won't be you wanted the current over here, right? So my bad, it's C1 R1 by C1 by 1 by C1 R1 R2, and not C1 R1 by R2. So this is something that needed to be changed. And actually it's ulta of this. So L equivalent is C1 R1 R2. Okay. And in this case, what you get? You get C1 by GM1 GM2. So this is the L equivalent that you get. Now let's move to the original circuit. What we wanted to replace this inductor by that circuit that we made, and that circuit is called gyrator. Okay, there is a name to this circuit. This is called gyrator. Okay, so let's put this circuit in place. We have V in over here, we have GM times V in, that is pushing into the circuit. Then we have this capacitance of C. We have a resistance that we said we will have as 1 by GM. And then we put this gyrator over here. So this is GM1, GM2, and this is C1. Okay, so other thing that can be done. So now see, all these are made by. So on we have only transconductors, capacitors, and resistor. One resistor. So again, this is also something that can be built on integrated circuit without actually the use of integrator, without actually the use of inductor. Okay, now one thing that I will comment on over here is since all of them are made through transconductors and capacitors, so if there are transconductors, what happens is the values of these transconductances and resistance and capacitance are not always the same. Okay, due to change in temperature, due to change in let's say the operating voltage or whatever, due to some mobility, something can change, and the values of this components can change. Now what happens is, generally what happens is one kind of component change in a certain way. Okay, so if let's say all of these are changing in certain way and this resistor is changing in some other way, then your transfer function will become corrupt. Your transfer function, whatever you wanted, your maybe your bandwidth will change, or your frequency, center frequency that you wanted will change, and you can't do anything about it because you will have to keep track of so many different kind of components. So generally in an integrated circuit, it is preferable that you have similar kind of components. So let's see that if this resistor can be also replaced by some transconductors combination. So what do you have as this resistor? So you give some V to this resistor of 1 by GM, you get a current of V times GM, right? Now this current, again, we will follow the same concept that we used for this making this inductor. So what you can do is, so you basically want this voltage to get converted into current through a transconductor. So you can just simply, let's say you had this thing over here, a transconductor of a value GM. So if let's say V was given over here, what will be the current that will be flowing in this direction, ulta? If there is a bubble, this is a negative transconductor, so V by V times GM. So you want this current to flow from this node, and mind it, since transconductor is a voltage controlled current source, so while sensing the voltage, you always want high impedance. So the gate, the input of these transconductances are high impedance, and so if you want this current to flow from this voltage source, so you directly connect it like this. So this V by GM will flow from the voltage source. So your resistor is equivalent to a negative transconductor connected in whose input and output are shorted. Okay. So this way you can get a resistance also using a transconductor. Just a minute. Yeah. So just that circuit also in the circuit, that band pass circuit that we're building. You have C over here. Then how do you build that? GM and then the gyrator. You have GM2 and then this C1. Okay. So for simplicity, let's have both these as GMs only. Okay. Now let's see. So what was our claim? If we give input voltage over here, whatever voltage that is developed at this node, which originally had a parallel combination of R, L and C, now the R is replaced by this input output shorted negative transconductance, and L is replaced by this gyrator. So let's see if it actually behaves as a band pass circuit. So we will calculate its transfer function. So V in by GM is V in times GM is flowing over here. Now let's say this voltage developed over here is V naught. So your V naught will be equal to so the current that will be flowing due to this V naught is V naught times SC plus V naught times GM plus current that is flowing in this direction. So what is the current? So if this is V naught, this is V naught by SC1, and if this is V naught by SC1, the current GM times V naught by SC1, and if this is GM times V naught by SC1, the current that is flowing in the in this direction is GM square times V naught by SC1. Okay, so you have GM square V naught by SC1. So this is the total current that is flowing into all the components due to V naught, and what is coming inside this node is V in times GM. So applying KCL on this node of V naught, so we have V in times GM is equal to V naught by V naught times SC plus V naught times GM plus GM square V naught by SC1. So let's try to simplify this expression. V naught can be taken out common. So you have S square C times C1 plus GM SC1 plus GM squared divided by SC1. Correct? So what we want, V naught by V in, right? That is our transfer function. So we have SC1 GM divided by S square C times C1 plus S GM times C1 plus GM squared. Now this GM squared can be taken out common from this complete equation. So what we will have is we have over here is SC1 by GM divided by S square C times C1 by GM squared plus SC1 by GM plus 1. Okay. Now this is again our band pass filter, right? At very low frequencies, the filter will have at very low frequencies the S will become 0. At very high frequencies 1 by S square will become 0, and at the middle frequencies you will have a pass band. And where will be the pass band peaking? In original case it was 1 by square root LC. In this case it will be GM by square root C times C1. basically the 1 by square root of whatever is the coefficient of s square term. Okay, so this thing, so I hope it is clear that without an inductor you can actually build a band pass filter in an integrated circuit. Any doubts so far? Okay, so if there is no doubt, so that was it that I had from this lecture. Thank you guys for attending.